Hello everyone, I'm Matthew Hyzine, and today we dive into the intricate world of mobile applications and their often covert transmissions of sensitive data over networks. Join us as we explore Leak Semantic, a groundbreaking framework designed to address this pervasive challenge. Let's take a moment to outline the agenda for today's presentation. First, we have our background. We'll start by providing some context on mobile application security and the significance of safeguarding sensitive data in today's digital landscape. Next, we'll identify the problem in addressing the challenge posed by sensitive data transmissions in mobile apps and the potential risks they entail. Next, we have our details and methodology. Moving forward, we'll explore the intricate details of Leak Semantic, including its methodology and the techniques used in its development. Next, we have our limitations. We'll discuss the limitations inherent in our approach and acknowledging areas where the further improvements can be made. Lastly, next, we'll have the results. We'll present the results of each research, including the performance and effectiveness of Leak Semantic in detecting abnormal transmissions. Lastly, we have findings, where we dive into the key findings of the experiment and highlighting important insights gained through the research. And finally, we'll wrap it up with the conclusion, summarizing the key takeaways and discussing future directions for enhancing leaks. Starting off with the background information, mobile applications play a central role in our digital lives, facilitating various tasks while handling sensitive user data. However, amidst the vast sea of legitimate transmissions lurk those with malicious intent. They stealthily leak private information to unauthorized recipients. The core of the issue lies in two fundamental questions. How do we uncover these malicious transmissions within mobile apps? And once identified, how do we discern their legitimacy? This is where Leak Semantic steps in, offering a robust solution to these pressing concerns. This paper aims to spot these fake sensitive network transmissions in Android app. Well, what's the problem? The problem is traditional approaches have struggled to keep pace with the evolving landscape of mobile app threats. One of the primary reasons for this is the complexity of the Android API and runtime environment, which often obscures malicious activities. As a result, existing methods fall short in effectively detecting and mitigating these threats. One of the emerging tactics employed by malicious actors is to use a logic bomb within mobile apps. These logic bombs serve as covert triggers, allowing malicious transmissions to remain hidden until specific conditions are met. By receiving commands from remote servers, these apps can effectively disguise their true intentions and evade detection by traditional security measures. This poses as a significant challenge for security professionals as identifying and mitigating these hidden threats become increasingly difficult. Next, we have our details and methodology. At the core of Leak Semantic lies its unique combination of program analysis and machine learning. By leveraging a hybrid static dynamic analysis approach, Leak Semantic is able to uncover both normal and abnormal sensitive transmissions within mobile apps. This hybrid methodology allows Leak Semantic to achieve superior results compared to traditional static or dynamic analysis approaches, providing a more comprehensive understanding of network semantics. Leak Semantic's hybrid program analysis component is the cornerstone of its success. By seamlessly integrating static and dynamic analysis techniques, Leak Semantic is able to effectively uncover abnormal sensitive transmissions that may otherwise go undetected. This hybrid approach not only improves the accuracy of Leak Semantic's detection capabilities, but also enhances its efficiency, enabling faster and more reliable identification of hidden threats. In addition to its program analysis capabilities, Leak Semantic utilizes machine learning algorithms to further enhance its detection capabilities. By leveraging traffic data collected during the analysis process, Leak Semantic is able to build classifiers that can effectively differentiate between normal and abnormal sensitive transmissions. This machine learning component adds another layer of sophistication to Leak Semantic's detection capabilities, allowing it to adapt to evolving threats and provide more accurate results. Continuing methodology and details, we'll dive into methodology of hybrid program analysis. It's a powerful technique for comprehensively modeling app behavior. This approach combines both static and dynamic analysis to provide a holistic understanding of app runtime behavior, addressing the challenges posed by the complexity of Android apps. At its core, hybrid program analysis seeks to effectively model app runtime behavior by leveraging both static and dynamic analysis. But by combining these two approaches, hybrid program analysis aims to achieve comprehensive coverage of app behavior, providing insights into both expected and unexpected runtime scenarios. Now we're going to talk about the static analysis and call group construction. Linxomatic utilizes lightweight static analysis to pinpoint invocations of sensitive APIs and their corresponding components with Android apps. This initial analysis serves as a foundation for the subsequent steps in the Linxomatic framework. The construction of call graphs is fundamental to the understanding of structure and behavior of Android app components. Each component, such as activities or services, has its own lifecycle and event listeners, which are constructed from callback method. Linxomatic enhances the static analysis approach by assigning each component its own dummy main. This refinement improves analysis accuracy by eliminating confusion and streamlining the subsequent dynamic analysis process. Continuing the methodology and details, we have dynamic analysis in the unknown value handling. Linxomatic simulates the Android runtime environment to accurately model app behavior. By emulating core functionalities of the Android system, Linxomatic ensures that the dynamic analysis process reflects real-world app interactions, enhancing the effectiveness of detection. Linxomatic addresses various scenarios involving unknown values, a critical aspect for effectively detecting malicious behavior. Through meticulous handling of unknowns, Linxomatic enhances its capability to identify abnormal network transmissions and mitigate potential privacy risk. Next, we are going to talk about how Linxomatic handles unknown values. Linxomatic effectively handles unknown values as a crucial aspect for accurate detection of abnormal network transmissions. Conditional statements such as if statements often involve unknown values, leading to unknown branches during execution in Linxomatic. These uncertainties can pose challenges in accurately identifying abnormal network behaviors. To address these challenges, Linxomatic employs a depth-first search strategy by considering symbolic path constraints of unknown variables. Linxomatic minimizes the search space, enhancing its capability to identify abnormal transmissions effectively. When encountering an unknown branch, Linxomatic generates a snapshot of the executed state, including the program counter and memory contents, storing it in a stack. This snapshot mechanism ensures the integrity of the analysis process and facilitates efficient exploration of unknown branches. Each direction under the unknown branch is thoroughly explored, utilizing the snapshot to restore the environment post-processing. This meticulous exploration ensures a comprehensive coverage of potential transmission scenarios, enhancing Linxomatic's detection capabilities. Next, we'll dive into the comprehensive evaluation of Linxomatic, highlighting its effectiveness in identifying abnormal network transmissions. The evaluation of Linxomatic comprises of two main steps. Firstly, micro benchmark suites are employed to access its leakage detection accuracy. Secondly, real-world app analysis is conducted, followed by the construction of classifiers to differentiate between legitimate and illegitimate transmissions. Linxomatic's performance is benchmarked against established tools such as Adrubis, FlowDroid, and AppAudit. Through rigorous comparison, Linxomatic demonstrates superior performance in both micro-benchmark suites evaluations and real-world app analysis. The evaluation results underscore Linxomatic's superior performance compared to existing tools. Its advanced capabilities in identifying abnormal network transmissions offer promising prospects for enhancing mobile app security. Next, we'll address the limitations encountered during the development of Linxomatic. One of the primary limitations is the potential for adversaries to obfuscate flows intentionally, aiming to bypass detection methods. To counter this, future iterations of Link-O-Matic may require the integration of additional features to enhance its robustness against adversarial manipulation. Another challenge that was faced is path explosion, akin to what is encountered in concolic testing. The proliferation of paths due to unknown branches poses a significant hurdle. However, there have been implanted processing techniques to minimize unnecessary unknowns. Next, we have our results from the experimentation. Link-O-Matic outperforms other taint analysis tools, achieving the highest quality in detecting leaks in the DroidBench dataset. Its precise claw grabs and effective handling of unknown results in zero false alarms. While Andrubis performs well, Floydroid's over-approximation leads to lower precision, and it lacks runtime data generation for traffic flow analysis. App Audit, although similar to Link-O-Matic in approach, falls short due to its termination upon reaching a sync, limited handling of unknowns, and incomplete dynamic analysis implementation. Link-O-Matic superiority lies in its comprehensive dynamic analysis, support for Android-specific mechanisms, and accurate call graph modeling, contributing to better detection accuracy. Link-O-Matic, along with other taint analysis tools, struggles to detect flow involving inter-application communications, posing a challenge for detecting collision attacks. Additionally, control flow dependent taints remain an unresolved issue, a common drawback in taint analysis tools. In the BombBench benchmark, Link-O-Matic identifies the majority of leaks compared to other tools. However, Andrubis shows a significant decrease in accuracy, highlighting its limitation in handling complex program logic. For instance, Andrubis and App Audit fail to capture certain disclosure flows due to their handling of unknown variables, unlike Link-O-Matic. Floydroid also faces challenges in accurately modeling system functions, affecting its detection capability. Despite Link-O-Matic's effectiveness, it misses some flows due to variable implicity assigned by user-driven events, highlighting the complexity of handling unknowns and potential performance concerns. Lastly, we have our findings. The first finding for Link-O-Matic was that malicious transmissions in the dataset often utilize encryption to conceal host names, impeding transitional detection methods. A model trained solely on unencrypted instances shows significantly reduced accuracy when tested on encrypted instances. Now to review the findings from the research. Finding 1, malicious transmissions in the dataset often utilize encryption, about 69.7%. They use it to conceal host names, impeding traditional detection methods. Now to review the findings. Finding 1, malicious transmissions in the dataset often utilize encryption to conceal host names, impeding traditional detection methods. A model trained solely on unencrypted instances shows significantly reduced accuracy when tested on encrypted instances. The second finding was, while Link-O-Matic successfully identifies numerous malicious transmissions, it struggles with certain transmissions, such as those from the Droid Kung Fu 4 malware family, which dynamically retrieve host names from remote servers. Finding 3, some connections indirectly leak private data by first obtaining user coordinates from a legitimate server before transmitting them to suspicious servers. This highlights the importance of monitoring connections even when initially contacting legitimate servers. Finding 4, malicious HTTPS connections are not prevalent in malware, but authentic apps contain illegitimate HTTPS transmissions, primarily from third-party ads in analytic libraries. Future inspections of HTTPS connections may be necessary. And lastly, finding 5, many apps with legitimate sharing connections also include illegal transmissions for ad or analytic purposes. Users may unknowingly grant access to sensitive data, which is collected by unintended servers, as seen in the weather applications transmitting location data to ad services. In conclusion, Linksomatic has provided valuable insights into its methodology, evaluation, limitations, and key findings. Linksomatic emerged as a promising framework for identifying abnormal, sensitive network transmissions in mobile applications, addressing the shortcomings of existing approaches and offering enhanced accuracy through its hybrid program analysis and machine learning components. However, it is crucial to acknowledge the limitations of Linksomatic, including challenges with adversarial obfuscation and path explosion, which may require future iterations to overcome.